VRF full cooling. So first off, we've got the refrigerant going from the compressor, passes up to a reversing valve, and then we're going to send that refrigerant through this coil, changing it from being a superheated vapor to being a liquid with a tiny bit of subcooling. And from there, we're going to send that off and into this BC box. As that refrigerant comes into the BC box, it's going to come up to a gas liquid separator. At this moment in time, it's just an empty bit of copper. There's nothing really going on at the moment in time. We've just got liquid refrigerant passing into there. We're going to draw that liquid refrigerant off the bottom of that gas liquid separator via LEV1, and we're going to pass it into this tube-in-tube heat exchanger. And we're going to use this to subcool that liquid refrigerant. The way we're doing that is we're stealing a little bit of refrigerant that should be going through that tube-in-tube heat exchanger, and we're going to feed it through LEV3. So I've now got refrigerant that's dropped in pressure. It's now desperately wanting to boil. I pass that, say, a tube in a tube inside that to subcool it to around about 20 degrees. So the idea being is that when that refrigerant passes off to the indoor units, it's still actually 100% liquid as it goes through the expansion device. We run the indoor units as flooded evaporators. That is until they're within 2 degrees of set point. So I've got my subcooled liquid refrigerant. I send that off to my control valves. So I've got a set of control valves down here. A and C on this side, which are going to be open when I'm doing cooling, and valve B on the other side, which is going to be shut because we're not doing any heating. I send that refrigerant off to the indoor unit. I say it goes through the expansion device. We've got that big pressure drop, at which point it's now trying to boil at around about 0 degrees evaporating temperature, because we aim for that. That's how the compressor is being controlled. So 0 degrees evaporating temperature, or around about 7.2 bar. Passes through the expansion device on the indoor unit, boil it all off from being a liquid to all being a vapor, and we've got the vapor coming back. As the indoor units get to within 2 degrees of set point, it starts backing down the expansion device, which means the low side of the system starts getting lower, so it's going to go below that 7.2 bar, so down to sort of 6 bars, something like that, at which point we actually slow down the speed of the compressor to bring that back to 7.2 bars. So that's how we're controlling the speed of that compressor. On the basis the indoor unit's working fine, we've boiled that refrigerant all off from being a liquid to all being a vapor, and so I've got the return leg coming back into the BC box, and that passes back off to the outdoor unit. As that refrigerant comes back to the outdoor unit, next thing it comes to is an accumulator. This is acting as a buffer vessel, because at the end of the day we're ramping this system up and down, therefore we're not going to need all that refrigerant at all times. But it's also acting as a way of making sure that we've got vapor getting taken off the top of this, off to the compressor, so a bit of protection to make sure if there was any liquid to come back from the indoor units, it's not going to damage the compressor. We're also using it as a way of drawing some oil back for the actual compressor as well. So from the accumulator, off to the compressor, and then we start that refrigeration circuit all over again. VRF system in cooling only. So just a little quick overview here. This is the outdoor unit we're showing you here at this moment in time. So TH relating to thermistors, and CP relates to capillary, ST relates to strainer, SV for sonar valve, and LEVs are LEVs. Okay, we'll work our way through it. So off top of the compressor, there's TH4, to give you an idea of the actual discharge temperature. Normally somewhere between 50 to 90 degrees. If that TH4 sees temperatures in excess of 115 degrees, start slowing down the speed of the compressor to look after itself. If it gets to temperatures of 120 degrees, that's when we get an 1102 error kicking up, so it gives you an idea what's going on. Refrigerant passing from there, and it comes up to an oil separator. First 4 minutes of operation, SV1A is going to be open, so the majority of that refrigerant is going around in a little short circuit, so don't bother looking at it for the first 4 minutes. After that, SV1A will shut, and we'll use a capillary line to bring oil back from that oil separator. From there we pass up to 63HS, and we've got a pressure transducer there and a switch. So the switch is going to cut in if we see pressures in excess of 41.5 bar. And the other one is just literally a way of measuring the actual pressure on the high side. From there, that refrigerant is passing off and we're going to come up to our reversing valves. So we're using reversing valves to load up that outdoor coil as well. So in this situation, obviously they're both in the off position as we're doing cooling. And we send that refrigerant through the outdoor coil. Now how we decide the actual condensing temperature that we want to work with here is it looks at TH7, which is our ambient temperature reading, and it aims for that to be 10 degrees above that temperature. Therefore we can give off that heat. That's the whole point. Therefore we're condensing. That's also been used as part of the actual fan speed control as well, to control the head pressure control. By the time that refrigerant's passed through that coil, it will all gone from being a vapor to all being a liquid with a little bit of subcooling. Not much, like maybe 1 or 2 degrees, if that. That refrigerant's passing from there and off past my check valves and off to the BC box. I'll come back to the rest of the circuit in a second. So there's that refrigerant passing into the BC box. So this bit here is my BC box. And then I'm showing 4 indoor units here just to give you an idea. So there's that refrigerant passing into the gas liquid separator inside the BC box. So a bit looks like an enlarged bit of copper. And then we've got a tube-in-tube heat exchangers here. So we're using our tube-in-tube heat exchangers to do that subcooling. So I'd expect it to be around about 20 degrees at TH16. So it'll have gone from say 35, maybe even up to 40 degrees, depending on what the outside temperature is. Through those tube-in-tube heat exchangers, subcool it, I say, to around about 20 degrees. Now, I'm being very careful with these numbers because we've got an inverter-driven compressor and we've got an inverter-driven fan. So these temperatures are going to fluctuate. And the way that we're controlling this is via LEV3. So LEV3 is being used to bleed off some of the refrigerant that should be going to the indoor units and passing it through that tube-in-tube heat exchanger to subcool it. So that's the idea. And when it's doing this, LEV1 will be wide open because I want it's on full-on cooling, and these valves will be open as well. These two pressure transducers here, I'm not actually using those when it looks at the actual cooling side of things. I use those for heating. And we can get an idea of how well that subcooler is working by looking at TH15 and TH12 as well. So I'll give you other bits of information. So I'll say I've got a nice subcooled liquid passing off to the actual indoor units. As it passes through our expansion device, therefore we're going to go from the high side down to the low side, but we actually aim it so that if the indoor unit is more than 2 degrees from set point, this is actually a flooded evaporator. So although we had that big pressure change, and it's aiming for around about 7.2 bar, which is 0 degrees evaporating temperature, we're actually trying to have a flooded evaporator. And that is the case until the indoor unit gets within 2 degrees of set point. As it gets within 2 degrees of set point, we start backing down those expansion devices, giving yourself that individual control. And then you're going to end up with more and more, so we say, flash gas. Therefore, you're going to get higher and higher superheat at the end. But normally, I'll say if this is running as a flooded evaporator, I'd expect to see 0 to 4 degrees of superheat. So I'll say it's literally running as flooded evaporators. As it gets within 2 degrees of set point, I'd expect that to be near to maybe 10 to 15 degrees superheat. So the idea being was we're doing trim work at that point. And the way that we control the compressor back at the outdoor unit is it looks at that 0 degrees evaporating temperature, or 7.2 bar, and as I close down that expansion device, therefore you're dropping the pressure on this side to bring that pressure back up, I slow down the speed of the compressor. As I open out the expansion device to do more work, therefore the pressure changes on the other side of the indoor units, therefore I have to speed up the compressor to bring it back down to 7.2 bar. So that makes sense. So there's that refrigerant passing back. It should have all become a vapor. Comes back into the actual outdoor unit, past my low pressure sensing. So again, that's what I'm aiming for, that 7.2 bar. Back round, and we dump it into that accumulator. So accumulator is acting as a safety device to make sure I've only ever got vapor getting taken from the top of that accumulator and back to the compressor. It's also some way of storing the refrigerant, depending on how hard the system's working. And I'm also drawing oil out of the bottom of that accumulator as well. And we can look at TH5 and compare that to the low pressure sensing to get an idea of that refrigerant's actually all become a vapor as it's superheated. Just a little side note here. On these units here, the actual inverter is cooled with the refrigerant, so I'll bleed off some of that refrigerant that should have been going for the indoor units at this point here via LEV9, and I use that to actually cool the inverter itself. And it's only going to start doing that when the actual inverter gets decently warm. Anything above sort of 75 degrees, other than that, it doesn't actually touch it.